In this two-part video series, you're going to be studying the concavity of functions and points of inflection and what we call the second derivative test. So you'll find these handouts on the course website. You're welcome to print them off and or make your own notes. Please pause the video as you feel necessary in order to give yourself the chance to just to make sense and make some connections between what is being said and what you currently understand about functions and their derivatives. Okay, so let's start off with the definition for the concept of concavity. Okay, so we say that a graph of a function is concave up, that is concave upwards in a certain region over its domain if certain characteristics or criteria are met. And here are 4 nuggets of information that we're going to consider. So the first one is if graphs lie above all of the tangents, then a function is concave up in that region. If the tangents rotate counterclockwise, then a function is concave up. If the slope of your tangent line increases over that region, the graph is concave up. And lastly, if the first derivative, that is f prime at x, increases, or the second derivative at x is positive, then we can say that a graph of a function is concave up in that specific region. So just to emphasize some of these particular points, you can see that based on the tangents that are being drawn, okay, these 3 here that we have available to us, you can see that the graph is above the tangent lines. Okay, you can also see that the tangents are rotating counterclockwise. So as we read a graph from left to right, you can see how there's a rotation of the slopes of those tangent lines in a counterclockwise direction, right? Counterclockwise. We can also see that the slope of the tangent lines is increasing. Now what we mean to say by increasing is that if you look at the values of the slopes, -2, the slope of 0, and capping off with a slope of 3, what that means is that numerically speaking, if you're looking at a number line and each of these values represents a slope, what you can see is that beginning at a value of 2, or a slope equal to 2, then we can see that each slope to the right of that is larger than the one to its immediate left. So therefore, we have a definition for that particular bullet of information. That's this one right here. Lastly, what we're going to see is that when we perform, right, this is kind of the algebraic skill that we're going to be picking up later on. If we can then apply our derivative rules to determining intervals where the second derivative is positive, then we're going to be able to classify the concavity or describe the concavity of functions over particular regions of their domain. Let's move on down to the information regarding concavity down or concave down. These points are complete opposite to what we have above. So let's take a look at these. So a graph is concave down if these criteria are met. The graph is below its tangents. The tangents rotate clockwise. So that is rotating in this direction, like so. The slope of the tangent lines decrease, and yes, we can see that from 3 to 0, to -2. So in that case, it's moving counter to the direction we had established originally for concave up. And also, if f prime at x decreases, that is the slope of the tangents if they decrease, or if the second derivative has a negative value, then we can classify that region of the graph to be concave down. So let's move forward and use these ideas and perhaps a few more. Okay, we're going to come back to this in just a moment. I'm more curious about this example here to see if we can apply what we had just seen in the first example to see if something is concave up or concave down. Now, I would really encourage you to pause the video and then take a moment to figure things out for yourselves. Okay, what I would also encourage you to do is to either use inequality notation or a simpler version of interval notation to describe where the graph is concave up or down, or neither. Well, moving forward, let's have a look at your answers that you came up with, and we'll see if any other information is required at this time. So here we go. Let's have a look at these here. This is a solution set for being concave up. And if you think about all of the characteristics as were given before, we can begin to discuss the concavity with respect to what's going on here. So if we look at the interval, let's say, let's start with -5 and ending at -3, that would give us this interval here. So from here and over to -3. Okay, if you look at that portion of the graph that is here, we can say that that is concave up for a number of reasons. One, any tangent line to that curve would be below the curve. We could also say that the slopes are increasing. Okay, as we read from left to right, the slopes are increasing. There's 2 points that we had seen earlier. Think about the other points. Let's go back. Here they are. Okay, you can definitely see counterclockwise rotation of the tangents. As for the last fact, the second derivative at x being positive, that we don't see specifically. We don't have a function equation in front of us, so we'll save that for later on. So let's go back and let's review the answers once more. So if you can see this, that is, go ahead and double check the rest that have been listed. We have 0 to 3, so along this interval here, we should see concave up, and then also from 3 to 6, that is from here to here, we should see concavity from there to there. Okay, regions where it's concave down, okay, that is where the graph lies below the tangents, and then the tangents are going to rotate clockwise, and the slopes are decreasing for all of the tangents. That corresponds to all of these regions. Those regions here are concave down. Okay, so you might be wondering what happens here at these particular points that I'm just going to star, or just to write an X through. This one here is very special in itself, so that receives special attention, but you might be wondering what's going on there. We'll come back to that in just a moment. Let's just go back and review these points here. So when you're testing for concavity, be it up or be it down, please remember all of those particular points that were given prior to. And if we read the introduction, it says let f be a function twice differentiable so that the second derivative of x exists over the interval defined as ab. So if the second derivative is positive for all x that belong to values on that interval, then the graph is concave up on that interval. So these are just examples of concavity being in an upwards fashion on an interval AB. Okay, the opposite here is true, that if the second derivative is a negative value, then you should see the graph looking as such. So this is all are all examples of concavity in a downwards fashion. Last but not least, if you determine that the second derivative is equal to 0, okay, over the entire interval, that is from a to b, then you're looking at the graph of a linear function. Okay, that is where f prime at x is constant. Okay, so now that we have somewhat of a firm rooting in the definition of concavity and how it is spotted, what we do need to do now is to consider those points that I had starred earlier on, and then take all of that information and move forward and look at how we would address concavity from an algebraic point of view. Okay, because at the end of the day, what we're going to end up doing is assembling all of the stuff we've learned regarding concavity, maxes and mins, as well as increasing and decreasing functions, put them all together so that we can sketch graphs more accurately than we were able to in previous courses. Okay, we'll also split the video into two parts. I'll pick a point where it seems reasonable to do so, and then we'll move forward with the second video. So let's consider this here. If we have a point A, F at A, so let's say that on these sketches here, that any of these points here could be denoted as A, F at A. Okay, and even back on this graph here, any of these points here, let's just denote them as A, F at A. Okay, just to relate to this example here, we call these points inflection points. I'll just say that call them IPs for now. If the concavity changes, so if you switch from concave down to up, you have an inflection point. So this would be an IP. Okay, or if you happen to switch from up to down, again, this would be classified as an inflection point or an IP. Okay, so you can pause the video now and go back and just indicate on the graph for those starred or x'd out points that those are inflection points. But don't label the particular point that I had starred and made special note of as an inflection point. Okay, for now. So if we look further along here at this point, we say that there are PIPs, or possible inflection points. That is, every single inflection point can be characterized as a possible inflection point. It is up to us to determine the nature of that point. That is it really a point of inflection? And depending on the depth you go into with your mathematics beyond high school, you'll note that there are various types of inflection points. Okay, they go by names of saddle points, points of undulation, stationary points. There's a variety of different points that relate to the concept of inflection. Okay, but this is just a beginning into that. So those points will exist if the second derivative at x is equal to 0. Okay, this is important. Not if it's positive, not if it's negative. Plus and minus related to the concavity. Okay, if it's equal to 0, then we see a point of inflection. Or
Your attention, everyone, the custodians are going to be pressing the fire alarm and the intrusion alarm shortly. As the custodians are going to be
well,
pressing the
that's not going to help for our video. So let's finish part 1 here, and we'll begin part 2 following the fire drill. Okay, and then lastly, if the second derivative x does not exist, okay, that is, you can't differentiate the function 2 times, we're not going to be able to establish a point of inflection. Okay.